All right, good morning, everybody. I hope you're all doing well. I'm trying to stay healthy throughout all this craziness that is, the fall term. So just a couple quick announcements before we get started. So as a reminder, there is a review session today on graphing functions and their derivatives. That's something we'll be practicing today. So if you feel like you need more practice on that, I encourage you to stop by that. That will start at 5. And other than that, just a gentle reminder that your next chapter quiz is next week on Tuesday. So, okay. All right, if you're live streaming, we have lost the rest of class, so we'll wait a minute for them to log back in.
All right. Can you hear us, Athena?
Yeah, can you hear me?
Oh, no, reset all the settings, I think. Okay. So weird. Okay, can you hear? Can you say something again?
Yeah, can you hear me now?
I can hear you, but say it again. I'm trying to get you on this big.
All right, I'm just gonna keep talking until you can hear me.
Yeah, great. So not yet. Keep going.
What's up?
Okay, there we go. All right. Sorry again. That's so weird.
I feel like the great and powerful Oz all of a sudden just like the voice. All right, so are we good to go, William?
Yeah, you're good to go.
Awesome. Okay, well, I was rambling on to you guys before I realized you were frozen and then disappeared. So I'll take a step back. So I just wanted to remind you guys that there will be a review session tonight at 5 o'clock that William's going to be doing on graphing functions and their derivatives. We're going to be adding on to that today with second derivatives. And so I think it'll be a really valuable session to keep practicing this type of work. So if you have the time, I strongly encourage you to hop onto that Zoom later and check it out. I also want to remind you that your second chapter quiz is coming up, and that'll be on Tuesday of next week. So that's what's coming up. Let's dive right in. Hopefully we can make up for lost time here. I'm going to switch over to the dot cam. So let's see, hopefully you guys are still there. Okay, yeah, there you are. So last time we started talking about the second derivative, we talked about why it might be important and what we might want to do with it with some application. And so today we're going to learn how to find it and what sorts of things it tells us and go from there. So in order to start talking about the second derivative, we need to go back and remember what we learned about the first derivative. So we're going to start with an exercise here where we have a function graph below. And we want to determine from this function the intervals where the first derivative is positive, negative, and 0. So that's what we were doing back in 2.2, right? So what do we need to look at on the original function to figure out the sign of the first derivative function? So we're going to do that. And then once we have those intervals, we're going to take a crack at actually drawing the first derivative. So that's something we also started practicing in 2.2. But we need to do this work to remind ourselves of how we go from the original function to the first derivative. So what I'm going to have you do is I'm going to have you try this out. Try to label the places in interval notation where the first derivative will be positive, negative, and 0. And then go ahead and try to graph the first derivative of this function if you feel confident in your intervals. So I'll give you about 2 or 3 minutes to try to write those down. Feel free to check in with someone next to you. And if the undergrad Ts are there, they can walk around and answer questions you may have. All right, take about 30 more seconds to finish up whatever part you're working on. All right, so hopefully you remembered a little bit from when we were doing this work 2 classes ago. But typically the first thing you want to do is find the zeros of the derivative. So the places where the first derivative will equal 0. And that for us is going to happen whenever we have a horizontal tangent line. So we notice that there's one here at x equals 0, and then another one over here at x equals 4. And part of the reason why I always recommend we start with the zeros is because typically when we're going to break up a function into intervals, the way we break it up is by where the zeros are. That sort of gives us the ending point of our intervals. So I want to remind you that what we're looking for on this original function is where we are increasing and where we are decreasing. Okay, so we're going to start off where we're increasing. And the reason why we want to look for that is because of this relationship that the first derivative is going to be positive when f of x is increasing. Okay, so that's going to help us answer this question about where the derivative is positive. So looking at this function, I can see that I'm increasing until I get to 0. So I can write that as negative infinity comma 0. We talked about how we need to use the open brackets here because at 0, we are constant, right? So we're not including 0 in the increasing. That's its own sort of category. And then we're also increasing over here. So starting at 4 and going on, we are also increasing. So these are the places where my first derivative is going to be positive. Similarly, when my function is decreasing, so going in the downward direction, that's going to tell me where the derivative of this function is negative. So f of x is decreasing. So we can see that that happens in this interval between 0 and 4. Okay, so as a reminder, and this point is incredibly important, when we are going from a function to its derivative, we are looking for where that function is increasing or decreasing, right? And that's going to tell us where the derivative is positive or negative. Positive and negative are different things than increasing and decreasing. If you look at this particular function, f of x, this function is negative almost everywhere except for 0 because it's below the x-axis. Okay, but the fact that this function is negative doesn't impact where the derivative is positive or negative, right? The only thing that impacts it is where we are increasing and decreasing. So we have to make sure that we have those two concepts of positive, negative, increasing and decreasing sort of well defined in our mind so that we remember what they mean, okay? And so once we have those meanings down, we need to remember on the original function, we're looking for increasing and decreasing. And what that tells us on the derivative is where it's positive and negative. Okay, so if we're going to graph this based on what we know and what we learned 2 classes ago, we know that we are going to be positive from negative infinity until 0. And again, if we're positive, we're sort of up here above the x-axis. And then also from 4 to infinity. So over here, we also know that we are going to be negative on our derivative between 0 and 4. Okay. And then finally, we know where the zeros are. So at x equals 0, the derivative value is 0. And at x equals 4, that derivative value is also 0. Those are the 2 places where I had these horizontal tangent lines. And then if I remember what I learned last time, I want to come through the zeros, make sure I'm in the right sort of general area, and I get something that looks roughly like this. So again, we talked last time about how to make it more accurate. We could draw in tangent lines and get the exact values to plot points. For now, we just want to look at the general shape because we want to use this to now segue into the second derivative. So it's enough for now to know that the general shape is this U shape and it hits all the properties we need to based on what we did up here. So again, that explores the relationship between the original function and the first derivative. So what we're going to do now is we're going to take this first derivative and we are going to make it sort of our original function, if you will. And so what does that mean? Okay, so I sort of regraphed it up here, right? So this is what we had before. I just kind of regraphed it up here. And so what we want to do is we want to do the same analysis on this function to talk about its derivative. Okay, so we're going to treat this as an original function in that we are going to consider where this function is increasing, decreasing, and has a horizontal tangent line so that we can then talk about the derivative of this function. Okay, so what I'm going to do is I'm going to give you another couple minutes. And again, I want you to look at this function here and determine where the derivative of this function will be positive, negative, and 0. Again, based on where this is increasing and decreasing and whatnot. And then I want you to take a stab at, graphing the derivative of this function based on what we know here. Okay, so take about 2-3 minutes, see if you can work that out, doing the same type of analysis we just did on the first function, but now we're going to do it to this function, and then we'll go through it together. Okay, take about 30 more seconds to finish up whatever part you're working on. All right. So again, I think it's really helpful to find the zeros first so we know how to split up our intervals. So here we can see we have a horizontal tangent line that looks like it happens at roughly x equals 2. And again, that is the point where we're changing from either increasing to decreasing or decreasing to increasing. That's when we find most of these horizontal tangent lines. So now we want to look at this graph and figure out where are we increasing and decreasing. So we can see that our graph starts off decreasing from left to right. It's coming in downward. And so we know that when we're decreasing, the first derivative will be negative. So the interval where we see that happening, we have negative infinity until 2, again, open brackets. And then after 2, we can see the graph go back up. So we're going to be increasing from 2 to infinity. Okay, so I talked about how we're treating this as an original function. So I wrote these statements as though this was f of x, and we're talking about f prime of x. But I want you to remember in the back of your mind, because we're going to come back to this in a minute, that this is the first derivative of the function we looked at before. So this is a derivative graph. And so we could call this f prime of x and then talk about f double prime of x. That's sort of the connection we're going to make in a few minutes. So just kind of keep that in the back of your mind. So when we think about graphing this function with these conditions, again, we know that we're going to be 0 at x equals 2. So we want to draw in that 0 first. And then we know that we are going to need to be negative before 2. So that means below the x-axis, and positive after 2. Okay. So we know from our lesson back in 2.2 that our function, that if we have a U shape, that turns into a linear function, right? That goes through our 0. And so here we can see that our line has to go from below to above. So when we sketch that in, it's going to look something like this. Okay, again, this is just an approximation. If I wanted to be really extra careful about it, I would do a couple of tangent lines to get exact points to figure out exactly what the slope is, but that's not the focus of the exercise right now. So right now we're looking at the general shape. Okay, so again, because this was the first derivative picture and I took the derivative of it, this would then be the second derivative of the original function that we looked at. So what that tells me is that I can go ahead and have the same relationship between the first derivative and the second derivative that I had from an original function to a first derivative. Okay, so how do we write those out a little more formally? So since f double prime of x is the derivative, we know that if the derivative is increasing, then the second derivative is positive. And if the derivative is decreasing, the second derivative is negative. And if the first derivative is constant, so again, we have that horizontal tangent line, that's where the second derivative will be 0. So we have the same set of rules that we had before, but instead of going from the original function to the first derivative, we can use this to go from the first derivative to the second derivative. Okay, now this gets a little complicated because now we're using the first derivative in 2 different ways. Okay, when we had the very first original function, we were concerned with whether the first derivative was positive or negative, right? So we use the original to determine where the first derivative was positive and where it's negative. When we use it here, we are now concerned with where the first derivative is increasing or decreasing. So now we're using it in a different way. So what I want to say about that is it's really important to know what information you're starting with. Are you starting with an original function or a first derivative? And what kind of information you want, right? Because if we have a first derivative function, we can talk about the original function, or we can talk about the second derivative. And how we do that is different depending on what we are trying to figure out. Okay, we'll talk a little bit more about organizing those relationships in a few minutes, but we now have a relationship between the original and the first derivative, and the first derivative and the second derivative. So there's one relationship that we have not looked at yet, and that is the relationship between the original function and the second derivative, right? So that'll sort of complete our loop here. So here was the original function we started with, okay? And here's the picture of the second derivative. Okay. And I want you to take a minute and I want you to see if you can observe any sort of characteristics of the graphs that may be related, right? So just like before, we were looking at increasing, decreasing, positive, negative, those sorts of things. I just want you to look at these pictures, take a minute, see if you can figure out if there might be a relationship. There is. See if you can figure out what it is. We'll talk about it in a minute, but I want you to sort of just take a look at it for a few minutes to see if you can figure it out. Okay, so how do we even start to do this kind of work, right? Is there a relationship? So I'm really noticing here in the second derivative a lot of things that I think could be helpful. So the first one is that the second derivative is increasing everywhere, which means that if we were looking at the second derivative in terms of increasing, decreasing, then whatever characteristic that would relate to on the original would have to be the same everywhere. And when I look at the original function, I don't see anything that's really the same everywhere. I can see that it's negative, but it's also zero. It increases, it decreases, it's concave up, it's concave down. So that doesn't really help me get any further. The other thing I notice about my second derivative is that part of it is positive and part of it is negative, right? So over here, I'm positive. Over here, I'm negative. And I see that that changes at 2. So what I want to do is I want to look at my original function and see if anything changes at 2, right? Because that's where this changes. And so if I think about increasing and decreasing, that doesn't fit, right? Because I'm increasing and decreasing before 2 and increasing and decreasing after 2. However, what does happen, and you may or may not have remembered that this is a characteristic, is that the concavity of the original function is different to the left of 2 than it is to the right of 2. So what I notice is that to the left of 2, my function is concave down. Okay, so concave down looks like a frown. It's like a hill, it bends downwards. And to the right of 2, my function is concave up. Okay, it's not a coincidence. And if you were to do several other graphs and find their second derivatives, you would notice that this relationship is always true. So this relationship between the original function and the second derivative, the way we write it, is that if f of x is concave up on an interval, then the second derivative is positive on that interval. If the original function is concave down on an interval, then the second derivative is negative on that interval. And then finally, if the original function is at an inflection point, then the second derivative is 0 at that point. So what is an inflection point? So an inflection point is where we change concavity. Okay, so at the inflection point, you are not concave up or concave down. That's the point where we're changing, so it's neither. And so at that point, that's where the second derivative is 0, because that's where we're changing our sign. Okay, now just like the other statements, these relationships work in both ways. So if I had a picture of the second derivative, I could use the information about where the second derivative was positive or negative to determine where the original function was concave up or concave down. Just like if I have the original function, I can use the concavity to determine the sign of the second derivative. Okay, so now we have three sets of relationships: the original to the first derivative to the second derivative, and the original to the second derivative. These are the ones that we need to practice and get really good at so we understand all the different mechanics of how they interact. And it's a lot to keep straight at first. We're going to do some practice problems, and then we'll talk about how we might organize our thoughts on this. Okay, so let's try to put this into practice a little bit. So here we have a function, okay, f of x. And what we want to do is for each of the values here, so at 2, or I guess -2, 0, and 2.5, we want to determine if the original function, the first derivative, and the second derivative are positive, negative, or 0. So part of organizing our thoughts is really just understanding what we're being asked to find. So when you're asked to find a functional value, right, that's the y value. So we're asking, is the y value positive, negative, or 0? When we look at the first derivative, again, slope of the tangent line or increasing, decreasing. And then second derivative, we're looking at concavity, concave up or concave down. So for each of these, so at -2, at 0, and at 2.5, we want to find the sign, so positive, negative, or 0, for each of the types of functions we're looking at: the original, the first derivative, or the second derivative. So I'm going to draw in a couple points on this graph to help us. The first thing I'm going to do is I'm just going to label where the point is. So this is our -2. 0 is here. And then 2.5.
Adina?
Yes.
Oh, we lost you for about 20 seconds.
Okay, so saying I'm going to label some points here to help us do this particular problem. So 2.5, we'll call that here. Okay, so this is -2, this is 0, this is 2.5. I'm also going to label the inflection points in black, so you can kind of see where we're changing, right? They're all going to happen right at the origin here. So hopefully that will be helpful. Okay, so take 2 minutes. Again, try to determine if each of these things is positive, negative, or 0. And this is really making sure you understand the difference in how we analyze each of these things on an original function. Okay, so take 2 minutes and then we'll go through it together. All right, take about 30 more seconds to finish up whatever part you're working on. All right. So for the first three little problems here, we're trying to figure out what's going on at negative. So we start with f of -2. So again, this is the functional value. So if we look at the y value at -2, we can see that it's going to be something like, I don't know, -0.5, but we can see that it's below the x-axis. So since the y value is below the x-axis, whatever it is, it's going to have to be negative. Okay. For the derivative at -2, we have two ways we can figure this out. We can either see that this is decreasing, right, and use that to say it's negative, or you could sketch in the tangent line and see that the slope of the tangent line is negative. So either of those are fine, but now we see that the derivative at -2 is also negative. And then finally, we're looking at the concavity. So here for the second derivative, we want to figure out, are we concave up, concave down, or at an inflection point? So at -2, we can see that we are concave up. Okay, if your second derivative is concave up, we said that that means the original, well, we said that that means that the second derivative will be positive. So here, that's going to be positive. So at this particular point, we have a negative functional value, a negative first derivative value, and a positive second derivative. Okay. What's really important is that if one of these is negative or positive, that doesn't really impact whether the other ones are negative and positive, because we're checking for different things for each type of thing we're looking at, whether it's the function, the derivative, or the second derivative. So let's go ahead and take a look at the next one. So here we're at 0, so we're at this point up here. So we start with the functional value, f of 0. So we can see that f of 0 is up here at 1. The actual value is 1. But since we are above the x-axis, we can see that that is positive. When we think about the derivative, we see that we have a horizontal tangent line here. So that derivative is going to be 0. And then to talk about the second derivative, we need to look at the concavity, and we can see that here we're going to be concave down, right? So it's like a hill. And since we're concave down at 0, that tells us that the second derivative is going to be negative. Okay, so finally, let's see what's going on at 2.5. So we start with the functional value. So here we can see that it crosses through at roughly 2.5. So that value is going to be 0. For the derivative, we can see that we are increasing here, right? And if you were to draw on the tangent line, you could see that it would be positively sloped. And then finally, for the second derivative, we can see that this is going to be the same point as the inflection point, which means that the second derivative is also 0. So one of the things we want to get good at is taking any function and picking a point and talking about whether the function, the derivative, or the second derivative is positive, negative, or 0 at that point. That's just a good way to start practicing this. I just picked 3 points that were interesting, but we could have done it at 4 or -3. So we could pick any other point or any other picture to do the same type of work. Okay. Another way that this comes up for us using these relationships is when we have tables. So the next example we're going to look at, we have 2 tables below. So the first table is a table where we have values of the original function on the table, and we want to talk about the concavity of that original function. So in order to be able to do that, the first thing we're going to need to do is to approximate the first derivative on the table. Okay, because we need to have the first derivative to talk about the second derivative so that we can then link that back to concavity. So as a reminder, the way that we approximate the first derivative is by doing average rates of change. So we could do the average rate of change to the left and the right and then average them together, or we can do the shortcut where we average the numbers around them to get that value, but we need to get that approximation. Once we have an approximation for the first derivative, we can look at where the first derivative is increasing and decreasing to help us learn more about the second derivative, which will lead us to concavity. So there's a lot of steps here. The second table I'm going to ask you to look at has derivative values. So this is a completely different function than the first one. So we're going to look at these derivative values. So we have the first derivative. And so if we have the first derivative, how can we then use that to talk about the second derivative and thus the concavity? So this is what I want you to think about in this particular problem. There's a lot of calculation and a lot of analysis that needs to be done. So I'm going to give you about 4 minutes. And again, you want to start by approximating the first derivative. And then once you have the first derivative, either by approximation or because it's given, you need to consider where it's increasing and decreasing to then start to link it to the second derivative. Okay, so take about 4 minutes, see what you can figure out from these tables, and see what you can figure about the concavity of the original function. All right, take about 30 more seconds to finish up whatever part you're working on. So again, we want to start by finding an approximation of the first derivative when we have a table, right? If we had a graph, we could just look at where it was concave up and down, but with data is tricky and you can't always tell what it's supposed to look like until you have some more information. So we approximate the first derivative for every point, and I just did an example of one of the points just to remind you how we might use the shortcut. So if I want to approximate the derivative at 3, I can use the 2 points around it. So 10 minus 3 over 4 minus 2 gave me this approximation of 3.5. It would be the same if I did the left hand and then the right hand and then average them. This is just a little bit shorter. So once you have your approximation for the derivative, as I mentioned, we want to look at where this is increasing and decreasing. So here, if I'm starting at 2, 2.5, 3.5, those numbers are increasing, right? And then if I want to look at where we're decreasing, let's see, 3.5, 2.5, 1.5, 1. So this is the place where we are decreasing. And then I notice that at this tiny little interval in the middle, I stay constant. Okay, so again, increasing, I'm literally looking at these numbers, 2, 2.5, 3.5, those are going up, right? Decreasing, 3.5, 2.5, 1.5, 1, those are going down, right? So why do I want to know where my first derivative is increasing and decreasing? Well, the reason that's helpful is because my relationship with the second derivative is based on where the first derivative is increasing and decreasing. So if my first derivative is increasing, my second derivative is positive, right? That's the relationship I have between the first and second derivative. If my first derivative is decreasing, my second derivative is negative. And if my first derivative is constant, my second derivative is 0, okay? So that's leveraging the relationship between the first derivative and the second derivative. That's what I did in this step, okay? But wait, there's more, right? So now I want to leverage the relationship between the second derivative and the original function. So remember, if your second derivative is positive, that tells us the original function is concave up. So on this interval where the second derivative is positive is a pretty good approximation for where the original function will be concave up. Similarly, when the second derivative is negative, that's going to give me my approximation for where the original function is concave down, right? And we usually describe this with the x values. So we'd say concave up from 1 to 3, concave down from 4 to 7. And then we also know that the most likely place for an inflection point is between 3 and 4. So somewhere between 3 and 4 is where we're going to have our inflection point. So this has a lot of steps. We needed to get an approximation of the first derivative. Then we needed to write down what we knew about the second derivative based on the first derivative. Then we had to take that sign of the second derivative and link it back to the concavity of the original function. So there's a lot of steps and a lot of places where we could sort of go wrong. But if we're really careful, we're able to come up with some really good analysis of what's happening in the original function, okay? The second table is a little bit easier, right? Because the second table, we have the first derivative, so we can skip the step of calculating the first derivative and jump right to the step of figuring out where it's increasing or decreasing. So here, I start at 2, 5, 6, 12, 17. Okay, so that's increasing. Okay, and then starting at 17, I have 17, 14, 11. So right there, I start decreasing. Okay, again, if my first derivative is increasing, my second derivative is positive, And if my second derivative is positive, that tells me that my original function is concave up. Okay. Similarly, if my first derivative is decreasing, that tells me that my second derivative is negative. And if my second derivative is negative, that tells me my original function is concave down. Okay. The other piece of information that is sort of hidden here is that at this value, where I'm changing from increasing to decreasing, is roughly the most likely place to have an inflection point, right? So that in order for me to change from positive to negative, I have to go through 0. So somewhere near 5 is where I'm going to have an inflection point. That's my best guess for that. So that's sort of the type of work we do with data to try to talk about what we think is happening. Again, these are our best guesses when we have tables because we don't know what's happening in between these points, right? So they're not quite as accurate as a graph or an algebraic function, but we can still have a good general idea of what's happening. So before we go into the next section, which is marginal analysis, I do want to take a minute to talk about how do we organize and keep straight all of our thoughts about these relationships between the first derivative and the second derivative, right, and the original function and all of these things. So let me, oh good, let me get a blank piece of paper. There's conveniently one here. So one of the things I recommend that I think will be really helpful if you think you would need help keeping these straight is to create a chart. Okay. And in this chart, we're going to label f of x, f prime of x, f double prime of x, and then at the top, f of x, f prime of x, f double prime, right? And in your chart, what you want to do is along the left side, we're going to write something like, if we have this, and then up here, then we know this. Okay, so what does that mean? So if we are given information about f of x, what would that tell us, or how could we use that to talk about f prime of x? Well, if we have f of x, then we would say something like, if f of x is increasing, then the derivative is positive, right? So if f of x, then f prime of x, okay? Similarly, the same statement, if we have f prime of x, so if we have a table or a graph or a statement about f prime of x, so if f prime of x is positive, then f of x is increasing. Okay, so these are the same statement, but it really depends on what information you have in which direction you're going to use it. The benefit of organizing it this way is if you then are given a graph, a table, a function of f prime of x, then you would just cover the other 2 rows so you couldn't see them somehow with paper or whatever, and you would just look down the row to figure out how to use it. Okay, so if you have f prime of x, and I'm asking you to tell me about f of x, you're using this box. This is how you're going to look at it. If I've given you f prime of x and I'm asking you to talk about f double prime of x, use this box. It helps you organize the direction that you are going to use the statements in. And taking the time to fill out the chart will also help you understand how these relationships work. Obviously, we're just going to put an X on the things that relate to itself, because if you have f of x and you're talking about f of x, you're not really doing much, right? But by writing in the statements in the right direction in terms of their relationship will not only help you understand, but also give you a quick reference on how to do it. If you start to feel flustered during a quiz, you can just pull out your chart and say, okay, I have this graph of the second derivative, and the answers are all asking me to talk about the original function. And then you look at the statement and it says, if the second derivative is positive, the original function is concave up, right? Then you can quickly figure out how to apply these different rules. So I encourage you to make one of these if you think it'll be helpful. I think typically it is helpful, but it's up to you. Okay, so that's how I recommend organizing this. So let's see, going back. Oops, hold on, I put my notes over here. We are now going to move into marginal analysis. So we actually talked about marginal analysis before when we talked about cost and revenue and profit. And the thing I said then was, hey, for right now, we're assuming everything's linear, right? That was our deal. We said, okay, marginal cost is the slope of the line. Marginal revenue is the slope of the line. Marginal profit is the slope of the line. But now we have ways to talk about how functions are changing that are not linear. So we're going to refine our definitions and just make sure we can then apply what we've learned in chapter 2 to cost and revenue functions, right? Because they operate mostly the same, but a tiny bit differently. So let's talk about this. So marginal cost, which we write as C prime of Q, so the derivative of cost, is the additional cost to produce one more item. And we can estimate this by, looking at the difference between the cost to produce a certain number and the cost to produce one more, right? And so this sort of approximation, which comes from economics, is a little bit goofy because we know that when we approximate the derivative, we're approximating with an average rate of change. And they write it this way, but it really is an average rate of change because on the bottom, we would do Q plus 1 minus Q, and the Q's are going to cancel. So it's really just divided by 1, right? And anything divided by 1 is itself. So you can write it this way, which is simpler because you're always just dividing by 1. But it doesn't really spell out that what you're doing is an average rate of change. Okay, so that's happening in the background. So one of the caveats here, right, is the marginal cost is the cost to produce one more item. And so when we talk about that, there is a directionality, right? So we're going from 10 to 11, or we're going from 15 to 16, right? So to produce one more is always looking at one to the right, which means that when we do any sort of approximation on the derivative, we are going to be doing a right-hand approximation. And there's one exception to that, which we'll talk about in a little bit. Okay, so unlike other general derivatives where we would do the left and the right and then average them, the default for marginal cost, marginal revenue, or marginal profit is always a right-hand approximation. Okay, so that's different, and that's sort of the little star note that we have to make here. But otherwise, everything that we've been doing is going to function the same way. So marginal revenue is the additional revenue from selling one more item. Again, it's the difference between selling 10 and 11, or between selling 20 and 21. And this again is divided by 1, so it's actually an average rate of change. And then marginal profit is the additional profit from making and selling one more item, right? And so we get that by looking at marginal revenue minus marginal cost at a particular quantity, okay? So what do we mean that we're sort of scaling this up to be nonlinear? Well, before we had linear functions, and we said if cost is linear, then marginal cost is the slope of the line, right? If you add one more in quantity, then the slope will tell you how much to go up. Obviously, now that we're nonlinear, right, then if we were trying to approximate the marginal cost at a point, we would be looking for the slope of the tangent line, right? We're approximating the derivative by approximating the slope of the tangent line in all the same ways we've been doing throughout chapter 2. Similarly, for marginal revenue, if you have a linear function, it's just the slope of the line. But if you have a nonlinear function, we're going to go ahead and try to approximate the slope of the tangent line at that point, right? To tell us how much it's changing at that point. So let's look at some examples. I just want to remind you that we want to take everything we've learned about approximating derivatives in chapter 2 so far and apply it to cost and revenue, with the caveat that if we are approximating, we are using a right-hand approximation. Okay, let's do some problems here. So start with example 1. Here we have revenue given in a table, and here we want to determine the marginal revenue at Q equals 15. Okay, so we are approximating R prime of 15 on this table. So again, we want to pair what we know about approximating on a table to what I just referenced about cost and revenue. So I don't know, take 2 minutes and try to approximate the revenue on this table at Q equals 15. All right, take about 30 more seconds. All right. So if we want to approximate marginal revenue on this table, again, marginal is the same thing as derivative. We're interested in what's happening at 15. So 15 is here. So to approximate the derivative, we are going to use the data to the right. We're going to do a right-hand approximation because in this problem, we know we're talking about revenue. And whenever we're talking about revenue and cost, we want to do a right-hand approximation if we are approximating. So we'll do a calculation over here. So we're going to do 180 minus 160 divided by 20 minus 15. Right, so that's going to give me 20 in the numerator and 5 in the denominator. So that simplifies to 4. Okay, let's talk about units for a minute. So we've been talking about units. Here, they are implied. So what does that mean? So revenue is always talking about money, right? The currency. And for quantity, if nothing is specified what you're measuring, we call it an item. So when we talk about the units of this, it's often written like this: $4 per item. Okay, so just so you know the context, again, usually with something per something, this is the dependent units is money or dollars, and the independent units are going to be per item. If you know the item, you can fill it in. So if we were talking about sweatshirts, maybe $4 per sweatshirt, right? So what does that mean? That means that when we are selling 15 items, right, that selling one more item will bring in an additional $4 in revenue. Okay. So again, the key things here, we want to approximate on the table using what we know about tables, but also because it's an approximation, we're going to do it to the right. Okay, let's look at another example. So for example, 2, we have a part A and a part B. So part A wants you to approximate the marginal cost at Q equals 10. Okay, so here we have a cost function. We are trying to approximate C prime of 10, right? So 10 is here. You can see this is supposed to be linear. Hopefully you can tell that this is linear. And then once we have C prime of 10 from part A, we're told in part B that R prime of 10 is 15. So now we will also have the marginal revenue, and we want to pair these two things together to approximate the marginal profit. Okay, so you have to do part A before you can do part B, but I'm going to give you 2 minutes. See if you can figure out what the marginal cost is going to be here, and then use that with the given marginal revenue to answer part B. Okay, so take 2.5 minutes. See if you can work that out, and then we'll go through it. All right, take about 30 more seconds. All right, so because our cost function is linear, we can revert back to the notion that the marginal cost is going to be the slope of the line. We don't need to worry about left and right because it's going to be the same everywhere. So we can just find 2 points on the line and find the slope when it's linear. So here I use the point 10, 150 and the point 30, 300. So depending on if you use the same points, you may be slightly different than mine, but should be roughly the same. So when I calculate the slope by doing change in y over change in x, I get 7.5. But you have to remember that we need to put this in context. So remember, cost is talking about money, right? And when we do marginal cost, we're talking about how much money it's going to cost us to produce one more item, so dollars per item. So 7.5 is actually going to be $7.50 per item. Right? So in math, we can always take off a 0 if we don't need it, but our currency system works differently. So we do want to add that 0 back in because it's $7.50. So you always want to keep 2 decimals whenever you're talking about money. So here for part A, we get $7.50 per item is our approximation. For part B, we have also given that the marginal revenue at 10 is $15 per item. And we want to know what the marginal profit is then. So marginal profit is marginal revenue minus marginal cost. So we wouldn't be able to do this if we didn't have the marginal cost from part A. So we have this marginal revenue that's given minus the marginal cost that we figured out, and that produces a marginal profit of $7.50. Okay, so what that means is that I will gain an additional $7.50 of profit if I make and sell one more item from 10 to 11. Okay, so that's going from 10 to 11. I'm going to gain an additional $7.50. Okay, now the next example we're going to walk through together because it's an example, but it's also how to do some of the analysis. We were probably not going to have enough time to do example 4. So I'm just going to point out that example 4 is local linear approximation, which we were doing last class, where we use information we have and the derivative to approximate another point in time. Okay, so that's how you do number 4. But number 3 is super important. So we need to make sure we see what's going on here. So number 3, the question itself is not super tricky, but there's a lot of other things that are happening. So consider the graph below and determine when this product is making a profit. Okay, so remember, profit is revenue minus cost. When we say making a profit, that means we want profit to be positive, right? Because we also have instances where profit can be negative. In order for profit to be positive, revenue minus cost must be positive. Okay, well, that will happen if revenue is greater than cost. So on this graph, we're looking for where revenue is greater than cost. So revenue is the line, it's the blue one, and cost is the wavy one that's red. And so we can see that the interval where revenue is greater than cost, to answer this part of the problem here, is between 130 to 215. Okay, so from 130 to 215, we have a profit. We're making a profit. Revenue is greater than cost. However, okay, one of the things we need to be able to do is to differentiate between when we're making a profit and when we are making the most profit, because we always want to land when we're making the most money. So notice here, roughly here, okay, is where profit is going to be maximized, because that is where there is the biggest difference between revenue and cost, right? So if you do revenue minus cost and the number is bigger at one point than another, you're making more profit here, okay? So one of the ways that this relates to marginal revenue and marginal cost depends on if you are to the left of this max profit or to the right of this max profit. So notice here that when I am to the left of the maximum profit here, my marginal cost is here, and my marginal revenue is here. So my marginal revenue, the slope of that tangent line, is greater than marginal cost. Okay, so in this area, marginal revenue is greater than marginal cost. The slope is bigger. So make more items. Okay, if my marginal revenue is greater than my marginal cost, I want to produce and sell more items because I want to get to this point right here of maximizing my profit. However, over here to the right, okay, over here, okay, we're still making a positive profit, right? However, we want to make less because we want to get back to this point of maximizing profit. And notice here that when you look at the slopes of these tangent lines, marginal cost is now greater than marginal revenue. So if marginal cost is greater than marginal revenue, do not make more items. Okay, so this is a little counterintuitive because we have positive profit all in here, everywhere between 130 and 215. However, The decision of whether or not to produce more items, to make and sell more items, depends where you are in this little bubble. And the way that we start to analyze this is comparing the marginal revenue and the marginal cost. So again, if marginal revenue is greater than marginal cost and you're in the positive profit sector, you want to make and sell more items so that you can get closer to maximum profit. However, if the marginal cost is greater than the marginal revenue, where we have positive profit, we do not want to make more items because that is lowering the amount of profit that we're making. Okay, so that's sort of a little tricky nuance within this problem that's going to start coming up. So make some notes about that that make sense to you. And then hopefully when you see this type of work on the homework, you'll be able to relate back to this particular picture to help you understand better. Okay, so don't forget about the Chapter 2 quiz next week on Tuesday. Stop in to drop in help today, tomorrow, Sunday, if you have any last minute questions, because Monday is a holiday.